Here we begin section 2, your first reinforcement learning program. In this section, we'll begin by taking a look at two different R packages that support reinforcement learning type tasks. We'll take a look at the MDP-Toolbox package, which supports reinforcement learning packages in a model-based framework using Markov decision processes. And we'll also take a look at the reinforcement learning package, which supports model-free reinforcement learning problems. We'll more closely examine the notion of state action and rewards. Then we'll begin an extended R example, traveling through a 2x2 grid to find the optimal policy and to compute the optimal policy using R. We'll extend this example, validating the policy, updating the policy through policy iteration, again using R. So here we begin the first video in the second section, finding optimal policy navigating a 2x2 grid. We'll discuss and compare the MDP-Toolbox and reinforcement learning packages. We'll present an alternative non-MDP representation of reinforcement learning, sometimes called a model-free approach. And we'll demonstrate a 2x2 grid world policy solution using R. Quick couple of words about the two packages. MDP-Toolbox is probably better known, and it was developed by these individuals that you see on the screen here. MDP-Toolbox is a Markov decision process specific approach to solving reinforcement learning. It's model-based, which means that you know the transition function, you know the probabilistic chances of actually executing an action when you take it. And actually, the MDP-Toolbox package was first developed by MATLAB people and later was ported over to R in this MDP-Toolbox package. In contrast, the reinforcement learning package developed by Nicholas Prolox is model-free. You don't know the transition probabilities, and we'll explain more about that later. Set up a simulated environment, and you have an agent, and you sample over and over and over again the agent's actions navigating through this environment, what state they're in, what state they move to, what their reward is. And you do this, say, 1,000 times or 10,000 times, and you collect the cumulative rewards, and from that you infer a policy, which is an optimal policy, which is the best action the agent can take moving out of any particular state into the next state. You'll see what I mean in just a moment. Frankly, the MDP-Toolbox R package is probably better known because it's been around longer, but frankly, it is not 100% dedicated to reinforcement learning type problems. It also supports linear programming problems, which may or may not be reinforcement learning specific. It uses the Markov decision process framework. Okay, in contrast, the reinforcement learning package, which was just released on April 17, 2017, is 100% focused on reinforcement learning problems. Now, we give you the documentation for both of these packages as PDFs released by the Comprehensive R Archive Network. You should take a look at this documentation if you're going to use R to model and solve reinforcement learning problems. This documentation is quite useful. It's got all of the functions that are supported. It's got lots of examples. It's got data sets. Take a look at it. So the key difference again, MDP-Toolbox is model-based and reinforcement learning is model-free. So here's a framework for reinforcement learning. We have our cute little robot here. This can be a robot. Generally, it's called an agent. It could be a person. And the robot is in an environment. In this case, it'll be a 2x2 grid. And the robot will enter the environment at any particular state and will take some action and move to a new state and will receive a reward for moving to that new state. So we're going to observe the agent interacting with the environment over and over and over again. We're going to observe which of the possible actions the agent randomly takes, what is the reward the agent receives, and that reward is, you can think of it as a signal about how well the agent is performing. And of course, our goal is we want to improve behavior given this limited feedback reward signal. We want to find the optimal policy for moving from state to state to maximize long-term rewards. Or you can look at it this way. The robot, the agent, is in some state at time t and has just received some reward for entering that state at time t. Then the agent takes a new action at time t, moves to a new state, moves to state t plus 1, receives a reward t plus 1. Do this over and over and over again. We observe the sequence of actions taken in particular states and the rewards that are received. So here's our particular environment or problem, and we want to learn the agent's actions and the rewards the agent receives as he's traveling through this 2x2 grid. So the notion here is that the agent can start out in any one of these states. We have 4 states, and there are rewards associated with entering each state. The rewards for entering S1, S2, and S3 are all -1, and the reward for entering S4 is +10. And that is, the actions that the agent can take in any state are to move left, right, up, or down. This is very similar to our grid world example. Note, for example, that if the agent is in state S2, tries to move left, bounces up against a wall and just goes back into S2. Or if the agent's in S2 and tries to go down, bounces against the boundary and ends up in S2 again. Notice also this red line separating S1 and S4, which is the goal and the high reward of +10. This means this is a boundary within the grid. The agent cannot move directly from S1 to S4, but the agent can move from S1 to S2, S2 to S3, S3 to S4. Let's spend the rest of our time, and we're going to use this relatively new reinforcement learning package that's up on GitHub. And so if you haven't already, and you likely haven't, you're going to need to install this package to use it. Really, the best way, since it's on GitHub, is to use the DevTools package. So first you need to install DevTools. I already have. You can do that by executing this function on this line. And then once you install DevTools, you use the DevTools install GitHub function to pull the package down from GitHub and put it on your machine. You only need to do these 2 commands on line 12 and 16 one time, and then you'll have the package on your machine forever. However, then you need to load it into your R session, and you do that using the library command. I need to do that right now, so I'll do that. Loading the package makes all the functions and data in the package available to you and to your R session. A key notion in Nicholas Prolock's package is that of experience replay. How this works is we observe the agent interacting with his environment. We learn the actions that the agent takes moving from state to state and the rewards that the agent receives. And this experience replay, we sample. Essentially, we set up an artificial environment, a simulated environment, and we sample the agent's actions over and over and over again in this environment. The agent begins in a state, transitions to a new state, receives a reward, transitions again to another state, receives a reward, and in this particular state, the goal is to get into state S4 and receive a very high reward of +10. So to model the environment, you need to build a function, an environment function, that mimics the characteristics of the environment. And here's the general template. The function takes in as formal arguments the state the agent is in, the action the agent takes, and it returns as a list the new state, the state that the agent moves to, and the reward that the agent has received by moving to that new state. Now, you can manually create your own environment function, or you can use canned environments that come with the reinforcement learning package. And we're going to use the latter. We're going to use this grid world environment that comes with the package. Or if you're new to a function, it's always good to query it. And you can do this. You can call up the help screen with the question mark. So take a quick look at what this does. The grid world environment defines an environment for the grid world example. Okay, and so these are help pages. They're always very concise and very useful in terms of understanding what you're doing, what the new function you're using does. So let's assign this grid world environment to env, and then we can print it out and take a look at it. So we do that. We execute it. Let's print out env. Now, over here in the console, it's kind of hard to read, so I've copied it over here into the text editor, into the script executor. So what's going on here? Okay, we're mimicking grid world environment. Takes in state in action, records the state that the agent moves to. Okay, so here are the representation of the actions and the new state that the agent can be in. If the agent is in state S1 and goes down, the new state is S2. If the agent is in S2 and goes up, then the new state is S1. If the agent is in state S2 and goes right, the new state is S3. If the agent is in state S3 and goes left, he goes back to S2. If this agent is in state S3 and goes up, the agent enters the goal state. Note that these are the only actions that the agent can actually take to move from state to state. For example, if the agent's in S1 and tries to go left, he ends up in S1. So you really don't have to model that explicitly in these if statements because there's going to be no change in state. There is no next state. Now finally, if the agent moves into S4 from some state other than S4, which is S3, then the agent receives a reward of 10. To any other condition, the agent receives a reward of -1. So you can see how we have modeled the environment, that we've modeled every possible action the agent can take and what the new state will be, and we've modeled every possible reward that the agent will receive from moving from state to state. And then what the function does, it just returns a list of the next states that the agent has moved to and the rewards that the agent has received. So that sets up our environment. We also need to tell what are the possible states. So we'll do that with a vector. And so we have states S1, S2, S3, and S4, and what the possible actions are, which are just up, down, left, and right. So we have an actions vector of the possible actions. So what we're going to do now is we are going to sample the agent's behavior 1,000 times. We're going to randomly place the agent into one of the 4 states and allow the agent to take an allowable action and observe the new reward the agent receives for moving to the new state. And the data that will be produced by sampling 1,000 times will be so-called tuples. That is, they will be sets, rows of observations that contain the state the agent was in, the action the agent took, the reward the agent received by taking that action and moving into the new state. These 1,000 observations will be stored as rows in a data frame structure. So we're going to use the built-in function sample experience to do that. Always a good idea to take a look at the help screen if you're not familiar with the function. And what we see is this is what it does. It samples, just to describe it briefly, it samples over and over and over again. These are the formal parameters arguments of the sample experience function that you can use to modify, to set up highly customized sampling experiences, arrangements with your environment. For right now, we only need to use these 4 arguments. So we're going to set loose the sample experience function, and we're going to capture the 1,000 observations in this data object, which is a data frame. These are the only 4 arguments we have to worry about right now. 1,000 observations, we're using our grid world simulated environment. States are states, that is S1, S2, S3, S4, and the actions are left, right, up and down. So we do that, we let that loose, and let's take a look at the head, the first 6 records in the resulting data set. And so these are tuples. We will input these into our reinforcement learning function, and you can see what it records. Okay, the agent was in state S3. The random action was to move right. It couldn't move right. There was a boundary, so he bounced back into S3, got a reward of -1. The next state is the same state the agent was in. Here the agent was in S2, moved right, which is a possible successful move, and he ended up in S3 and got a reward of -1. In fact, instead of just looking at these 6, let's look at more of them. I want to show you something in particular. So we're recording the state the agent was in, the action the agent took, the new state that the agent ended up in, and the reward that the agent received. Note, this is what I want to show you. Note that if the agent was already in the goal state, that is, we began the sample where the agent was randomly placed in S4 and randomly tried to take an action of up, which bounces against the boundary, puts the agent back in S4, there's no reward of 10. They only get a reward, they get a reward of -1. You only, in this simulated environment, as we saw, the agent only gets a reward of 10 when the agent moves from S3 up into S4, then the agent gets the reward of +10. Okay, so we have 1,000 observations. Think of this as just random sampling, from which we are going to infer the sequence of actions that the agent should take being in any particular state. And this approach is not new. This approach is similar to approaches taken to create models for random forests, for example. And one of the advantages of this approach is that you're creating a model of the optimal actions the agent should take, and you can test that or validate that against a new data set. So you can think of this, we're training the agent based on our existing data set, and then we can test the model on a new data set. So let's continue. That's our data. We do need to set a couple of control parameters, and we will discuss these more later, but the most important one is this one, gamma, the discount factor, set between 0 and 1. And what it does briefly is if it's set to 1, there's no discount. And what this means is as the agent moves through the grid, future rewards are counted as heavily as more current near-term rewards. If gamma is set low to, say, 0.1, it discounts the value of future returns, future rewards. They are discounted and weigh less heavily in the overall computation of the optimal policy. We've set the discount factor to be a middle ground, 0.5, but still that will weight the more recent rewards as the agent moves from state to state more heavily than future rewards. Now, just quickly, alpha is the learning rate. Again, can go from 0 to 1. It's set low, which means the robot will learn more slowly. And epsilon is related to the balance between exploration and exploitation. And we'll get into that later. We have set epsilon at 0.1, which means there's very low exploration. So anyway, let's do that. We can see we've set alpha, gamma, epsilon. Now let's get into reinforcement learning per se. Quickly, useful to look at the help screen. This is the function that actually does the modeling, the simulation, the observations of the best sequence of actions to take from moving from one state to a new state based on the rewards that are received for each action. And again, on your own, probably good. Take a look at the help screen for reinforcement learning. Okay, so let's do it. So we're going to execute this learning function on our data set, and it creates a model. Let's do that. It creates specifically a state action function model. Let's take a look at it. Now we can look at it directly in the console if we want to. We see it over here in the console. Note that each time you do this, it'll be slightly different because what we're doing is a simulation that converges on the cumulative rewards that the agent receives being in one state and executing some specific action over and over and over again. This is classic simulation where you simulate the possible results, you do it over and over again, and it converges on a number that probably best represents what the cumulative reward will be. And specifically note that the results we just got here executing it are slightly different from what I got previously, but they will be of the same magnitude. What the state action function means, it shows you in a numerical way, a scalar way, if the agent is in state S1, what is the future-looking cumulative reward that the agent might take based on whatever action the agent takes? Let's look. So he's in S1, he moves right. He can't move right. He bumps up against the wall, so he goes back to S1. The future-looking, the cumulative reward the agent probably will get moving right out of S1 it's negative. That's not a useful move. Similarly, if the agent's in S1 and goes up, again, the most likely cumulative reward is, again, negative. It goes left, same thing, because the agent can't go left, ends up back in S1. The only useful move is down, and that's reflected by the highest possible scalar reward among all of the choices of actions along this row. So this tells us S1, best policy, is down. Similarly, if the agent starts out in S2, going up doesn't help, moves back to S1. Going down doesn't help, bounces back to S2. Going left doesn't help, bounces back to S2. If you model this over and over again and record the rewards, the most valuable move or action is to the right, into S3. If the agent starts in S3 or ends up in S3, again, the most valuable action is up, 9.118. Going right doesn't help, bounces back to S3. Going down doesn't help, bounces back to S3. Going left is moving backwards, so that's even less valuable than going right or down, and so forth. Finally, note that the agent could start out in S4 or end up in S4 and try to take an action. There's no action that's useful from starting in the goal state. You've already got entered into there, hopefully from S3, and gotten a reward of plus 10. So all of the state action function values for actions taken while in S3 are all negative. Okay, now from this table, the reinforcement learning function infers the best policy, and so that's what we see here. The best policy is, if you're in S1, go down. If you're in S2, go right. If you're in S3, go up. And S4 really doesn't matter, but it turns out that right is a little less bad than all of the other choices. This is the most important output from the reinforcement learning function. This is the reward from the last iteration. Again, it'll be different every time and really is not that meaningful for our purposes. Okay, so next time we'll go through another example, updating this policy using the same reinforcement learning package. So what did we do in this video? We looked at the MDP-Toolbox R package as well as the reinforcement learning package. They have different approaches. MDP-Toolbox uses Markov decision processes proper, whereas reinforcement learning does not. It is a simulation sampling approach. We quickly described model-free and model-based reinforcement learning approaches, and we went through and extended our example to find optimal policy navigating our modified 2x2 grid world.